Okay, this is the first of 4 PowerPoints on Unit 3, and this one deals with intermolecular forces and separation techniques. I hope the little meme will make you laugh. We will talk a good bit about London dispersion forces. As you've talked about in the previous unit, Unit 2, which was on bonding, that there were 3 types of bonds, and we call these intramolecular forces, which is not our focus of this unit, but just as a reminder, we have to keep these 3 separate from the new topic of inter. They sound so familiar, so similar, but they're completely different things. So what we also will focus on is that no matter what kind of force is holding a substance together, these are going to determine their properties. So here are intermolecular forces, and notice inter means between molecules, and that's really the key. So when we talk about molecules, we're talking about things, substances like CH4 or water, and we know those are covalently bonded internally, but we're talking about how one molecule of CH4 would be attracted to a totally different molecule, or why one molecule of water would be attracted to another molecule of water. So these are the forces between the molecules. And intermolecular forces are definitely going to be weaker than our ionic, metallic, and covalent bonds. So again, just to keep it straight, a bond is intra within the molecule. These dotted lines represent the attraction between these polar molecules. And we'll get into the details of what these symbols mean. It's partial positive and partially negative when you have a polar molecule. So here are the types that we will focus on. And really to know what kind of intermolecular force one molecule would have as its attraction to another molecule, we first have to know if a molecule is polar or nonpolar. So this directly correlates with what we learned in Unit 2. So if you have a formula and you're not sure if the molecule is polar or nonpolar, that would require you to draw the Lewis structure, know what its geometry is, know if the geometry makes it be asymmetrical or of a symmetrical shape, and therefore know if it's polar or nonpolar. Once we know that, then we can determine which of these forces are coming into play between these separate molecules. So we'll start with London dispersion forces, and it is okay to use the abbreviations on AP questions, especially like free response. All molecules, polar or nonpolar, contain LDFs between their molecules. You will also see these just shortened to be called dispersion forces, and then really another term would be induced dipole, and we'll get into this on the next slide when we talk about really where these forces are coming from. So, but the most important thing here is to know that yes, polar and nonpolar molecules have these occurring between their molecules, but this is the only force of attraction between nonpolar molecules. Okay, so if we know we have a nonpolar molecule, the only force of attraction, I mentioned methane earlier, the only force of attraction between methane and other methane molecules would be LDFs. Okay, so what is really going on here? What happens is, and if you look at the graphic of this, it makes the wording of this probably easier to understand. If we have an atom, as we see neon here, I'm looking at A, and the electrons that are in the cloud in this atom just become unevenly distributed. Okay, notice you see the little symbols, partially negative and partially positive. So more of the electrons are always moving around the cloud and their energy levels. So what this is showing is that more of the electrons ended up in one area of the cloud than the other. So it caused this partial negative situation, which means the other end of the molecule would be partially positive. Because that's what they're calling an instantaneous dipole. Because of that situation, it causes the next atom or molecule, depending on what you have, to develop a temporary dipole. So basically, the partial positive of this first atom is attracting the electrons in the neighboring atom. So it's causing this second atom to develop a temporary dipole. So it's really a weak attraction between these temporary dipoles. So if we go back, induced dipole, it just means that these aren't permanent dipoles, they're just temporarily or instantaneously occurring. Now, if you're comparing two molecules and you're having to explain why the London dispersion forces are stronger in one molecule versus another, it's really about the number of electrons, and pi bonding also contributes to this, that are present in the molecule. What happens is if there are more electrons in the cloud has a stronger temporary dipole. What we call that is the cloud is more polarizable. And so that causes stronger LDFs between the molecules. And if we have stronger LDFs, and we'll get into properties, this is going to require more energy to break. Okay, so let me say that again. The molecule with the greater number of electrons, or if the only difference is a pi bond versus like a double bond versus a single bond, those two situations cause a more polarizable electron cloud and stronger LDFs between the molecules. Okay? Now, there is a case where, and we tend to say LDFs are the weakest, but there is a case at the bottom where LDFs could be stronger than dipole-dipole, which we'll discuss in a minute. Because if you have a really large molecule, it has so many electrons that those clouds are so polarizable that LDFs actually end up being stronger than some small polar molecules' attraction to each other. So we'll see that later on. The second type of intermolecular force are called dipole-dipole forces, and really the name tells you what the type of attraction is. A dipole means I have a polar molecule, and that polar molecule would be attracted to another polar molecule. So, as you see, the name tells you. The more polar the molecules, the stronger this attraction will be. Okay, so remember, polar molecules do have a permanent dipole and an uneven distribution of charge because they don't have dipoles that cancel, like in a nonpolar molecule. And notice the partially positive end of one molecule, like here, is attracted to the partially negative end of a different molecule. So this dotted line right here, that is our dipole-dipole force of attraction. And really, to think about it, why would one, and really polarity is covered in Unit 2, but just as a reminder, why would the hydrogen have the partially positive charge and the chlorine have the partial negative charge? That comes down to electronegativity, right? So remember, chlorine is very close in proximity to fluorine, which is the most electronegative element. So that's why chlorine is more electronegative here, and hydrogen is less electronegative and therefore partially positive. Now, hydrogen bonding is an unfortunate term because it's not a bond. Okay, it's really an attraction, but everyone calls it hydrogen bonding. If there was one term in chemistry I could change, it would be this. So you might see them called hydrogen binding forces. Again, we don't want you to think of this as a bond like an ionic bond. Okay, it is an attraction, and in fact, it is a type of dipole-dipole attraction, but this one's very specific. It's still between two polar molecules, okay, and here's the specifics of it. It's where there's a hydrogen in one molecule that's attracted to, and you can really see this down here with the water, to an F, O, or N of a neighboring molecule. So notice we have this hydrogen which has a partial positive charge, is attracted to F, O, or N, in this case the O, of a neighboring water molecule to its oxygen. That's a hydrogen bond. But the other part of this that is critical, and you have to remember this because there's a little bit more to it, is that this hydrogen must be covalently bonded to an FO or N. Okay, because what's causing this the FO or N, those are the three most electronegative elements. This is a very polar bond with the oxygen, so that makes that hydrogen have a strong enough partial positive charge, and therefore a hydrogen bond or attraction would be attracted to an oxygen on a neighboring molecule. Okay, so it is stronger than dipole-dipole, and again, just remember these specifics. Here are some examples. So if we had OH on one molecule, notice that's the dotted line, any fluorine on a neighboring molecule, that's a hydrogen bond right there. Same thing here. This hydrogen is covalently bonded to a nitrogen, therefore it would have a hydrogen bond, dotted line, to an oxygen on a neighboring molecule. So just different examples. This hydrogen is bonded to an FO or N. Notice this, in this case it's a fluorine. So it could form a hydrogen bond attraction to a neighboring molecule that contained a nitrogen. So it doesn't have to be like we see here. It doesn't have to be like water to water. It could be water to another molecule that contained the right, the correct elements. And then the last of the four major types of IMFs that we'll study are called ion dipole. Again, this name tells you everything. This is a little different. This is where we're going to have an ion attracted to a polar molecule. So really, a lot of these, the name does tell you. And this is a great example. When ionic compounds dissolve in water, soluble ionic compounds dissolve in water, they break into ions. And notice it matters how the water is attracted to that sodium ion. So our sodium ion is our ion in this case. And notice since sodium is plus as a positive charge, it's a cation, it's the partial negative end of the water, which is the oxygen end, that would point towards that. And if we had a negative, like if this was sodium chloride, and you were asked to draw, this would be a good time to practice this, how would we orient water around a chloride ion? So hopefully you would think, well, chloride is negative, it's an anion, so I would want to put the hydrogen end of water, if you want to do the ball and stick version. That's the O for oxygen, okay? Because the hydrogen end, that would be my ion dipole attraction right there. Okay? Partially positive hydrogen to the negative chloride. There are two other types. Ion, and I'll just actually skip to this one. That really isn't, I'll show you an example in the next slide, but that's extremely not common. But this we might actually see. So notice the name tells us what's happening. A dipole is a polar molecule, and an induced dipole is a nonpolar molecule. So we can kind of figure out. So a polar molecule attracted to a nonpolar molecule, that's not going to be a very strong attraction. Okay? Really, it says the strength of these forces increases with the magnitude of the dipole of the polar molecule and the polarizability of the nonpolar molecule. So a more polar molecule, and then with the polarizability of the nonpolar, that has to do with the number of electrons, which would increase the LDF forces. So if we look at these, here's our ion dipole again. Here's a hydrogen bond. Notice, and this is where you need to make a note of this, when you have a carbon compound, we don't really learn any organic chemistry in this class, but notice any carbon compound where you see an OH group on it, that is not hydroxide. When it's all nonmetals, that's a covalently bonded molecule. It's actually called a hydroxyl group, but that is a place. Notice it looks very similar to part of the water molecule where hydrogen bonding can occur. So be aware of that, okay? On this case, chloroform, notice it would have a tetrahedral shape, but it's not symmetrical because the three chlorines have a different electronegativity than the hydrogen. So it would be, it would have a net dipole, so it would be polar, and it couldn't hydrogen bond with the methanol. This is the same molecule as we saw in the previously. But since they're both polar, this is polar, this is polar, that's where we get that dipole-dipole attraction. This is the least common of the 6, ion-induced dipole. It's an ion attracted to a nonpolar molecule. Here's dispersion or London dispersion. Again, I told you it was fine just to call those LDFs. Notice this is octane and hexane, 2 nonpolar molecules. And also notice these structures. Anytime you just have carbons and hydrogens, expect those to be nonpolar molecules. So again, only carbons and hydrogens in a structure, that's going to be a nonpolar molecule attracted to another nonpolar molecule only through LDFs. Here is that on the previous slide we talked about how a nonpolar molecule, that's C6H14 hexane again, does have a slight attraction to acetone. Notice red is that oxygen, and that oxygen gives it a slight dipole. It makes it a little polar, and so that's the attraction between those two. So here's just a little learning check. What types of IMFs are expected between these molecules? And don't forget that if it is a polar molecule, we're going to have 2 answers. We'll have, like, if it's polar, remember there are 2 choices. So here I'll actually, just as a review, so we've got IMFs. Okay, if it's nonpolar, our only choice is LDFs. So that makes it a little easier. If it's polar, we have to decide, is it dipole-dipole or is it hydrogen bonding? But if it's polar, they both also have LDFs. Okay, so you just can't forget the LDFs are present with the polar molecules as well. So what type of IMFs are expected with these molecules? You need to draw the Lewis structure if you're not sure. So you need to think of, what is the shape? Is it symmetrical? Does it have a net dipole or not? The answer, I've actually used this, is nonpolar. It is tetrahedral, so our only answer would be LDFs. The next one, still tetrahedral, but that's going to be polar. So we have to think about what's that going to cause. So we had LDFs for this one. If it's polar, is it able to hydrogen bond? It does have a hydrogen. Is the hydrogen connected to the right element to be considered hydrogen bonding? And the answer is no. So we would say dipole-dipole. And you should have 2 answers there. LDFs. We can't forget that. And then the last one, this part of the chain looks very nonpolar, but remember what I just told you about this OH group? That makes it polar, and that is a site for hydrogen bonding. So that was going to be our primary attraction, and then LDFs are going to be a big part of it as well. And then you can review that on the next slides. Okay, so what's really the most important thing about these LDFs? Well, first we're going to focus on liquids. It's their properties. So when we mean physical properties, here's some examples. Boiling point, vapor pressure, melting point when we get to solids. So we'll talk about various physical properties, but what's causing high or low boiling points or high or low vapor pressure is how strong the IMFs are between the molecules. Okay, so for example, the higher the boiling point of a liquid, like water boils at 100 degrees Celsius, that is very high considering water is such a small molecule. So that indicates that water has strong IMFs between its liquid molecules, and we know now that those are hydrogen bonding. Now, when molecular compounds melt or vaporize, is IMFs that are broken, not the covalent bonds. Okay, and this is really important, and we'll keep talking about this. So notice when we say molecular compounds, these are things we draw a Lewis structure for. Okay, so when we say melting or vaporizing, we're talking about a state change. So if you think about water or ice melting, we still have water molecules. They're just in a different form, different state. If we vaporize water, like boil it, then we have steam, which is, it's just, they're still water molecules, but they're just separated. So is ice changing is ice changing to water a physical or chemical change? Remember, a chemical change is a reaction where you have new substances form. So hopefully you would think definitely physical, because what was happening there is ice is a solid, is this very regular arrangement. We've got to break some of those hydrogen bonds. Then we still have hydrogen bonding between the water molecules, but we've broken some of them to change the arrangement. Okay, so look at the melting points between nitrogen. Okay, so we'll find nitrogen. Nitrogen's melting point is 63. We could also look at its boiling point, okay, since we're going to talk about liquids. HCl, 188, and HF, 293. So notice whichever one of these is the highest for boiling or melting, that means it has the strongest IMFs. We just have to be able to name what kind of IMF is holding these molecules or attracting these molecules to each other. So that's really the task, and that's the one thing we're trying to learn how to do, is use this data, okay, these boiling point or melting point trends, to determine what kind of IMF is causing such strong attractions that HF, really has the strongest of all three. So really, if you just look at these, you might have to draw a list structure if you need to. These are simpler molecules, so maybe not. So N2 we should recognize as nonpolar. So what holds together nonpolar molecules? Well, the only choice there is LDFs, so that's why it has such the lowest melting or boiling point. It doesn't take much energy to separate. HCl is a polar molecule, but not eligible for hydrogen bonding, so we should indicate that there are 8 dipole-dipole forces between the HCl molecules. So that's why it has a stronger, higher boiling point or melting point, due to those are a stronger force of attraction in this case than the LDFs between the nitrogen molecules. And then last of all, HF is eligible for hydrogen bonding. It does have the highest melting point or boiling point due to the strong hydrogen bonding between the molecules take a lot more energy to break or separate. All right, now IMFs really play into how solutions form as well. So we learned, like in your first year chemistry class, that a solution is a solute dissolved in a solvent. Okay, you might have learned the phrase like dissolves like, and that works, but we really need to be able to go a little bit deeper in AP chemistry to explain really what that means. Okay, so like dissolves like, well, we could say a polar molecule dissolves in a polar solvent, or we could say a nonpolar molecule dissolves in a nonpolar solvent. Well, what's really causing that? Well, it's because of IMFs. So if you're asked why is this substance more soluble in water than this other one, you need to be able to recognize what IMF each substance is able to have with water. So, is ethanol soluble in water? Okay, well, I see carbons and hydrogens, but here's the big clue that tells me it's polar. So I would say yes, ethanol is soluble in water. The OH group causes a molecule to be polar and can hydrogen bond with water, making it soluble. So that's really, I can't just say it's polar, water's polar, they dissolve. I need to go further and be much more specific. This is what's expected for AP questions. That ethanol, because of this OH group, has the ability to hydrogen bond with water, therefore it's soluble. Now, CH4, we've looked at that earlier. Is it soluble in water? Well, we would think no. It really probably couldn't be because it's nonpolar. It could have some LDF attractions with water, but those aren't strong enough to make it soluble. And then lastly, when we talk about solutions and solutions forming, there's really 3 energy components here, and this really will go into much more detail in Unit 6. I just wanted to kind of give you an overall here, and this delta H is called enthalpy. What I really want you to start thinking about is that for a solution to form, there are 3 different things that have to go on. Okay, whatever's holding the solute particles together. Okay, like if we have an ionic compound, like let's say in it, we're going to put NaCl in water. Well, what has to happen for NaCl to dissolve in water? Well, think of that structure. All those attractions between positive and negative ions have to be broken. Anytime we're breaking an attraction, energy is absorbed, okay? And you'll get used to seeing this later, that's a positive enthalpy change, and it's kind of described at the bottom. But for right now, just know that energy is absorbed to break an attraction. And then number 2, we have a solvent that's attracted to each other. So if we think about water as our solvent, well, it has NaCl had ionic bonds holding it together. That's what had to be broken. Water has hydrogen bonding holding it together. And that, if the water is going to be attracted to something else besides itself, those attractions have to be broken. So again, we're really breaking a bond with ionic. With the second component of energy being absorbed, we're breaking IMF. So again, what I want you to understand here is that energy still has to be absorbed to break a bond or an attraction. And then lastly, and this is where it kind of all comes together, the attraction between a solute and solvent is what releases energy. So breaking a bond or an attraction takes energy. You have to add energy. The system has to absorb energy. If there's an attraction forming, it releases energy. And that's the main thing I wanted you to take away from that slide. So we see a bunch of pictures here. So here's our water molecule. Here's our crystal of NaCl. Is the overall solution formation endothermic or exothermic? Okay. Endothermic are the processes that absorb energy. I know you've learned that term previously. Exothermic means energy is released. So once I have these 3 things going on, I've got to break the hydrogen bonding here, I've got to break up this organized ionic structure. When these 2 attractions, these hydrated ions as you see in those pictures, that's releasing energy. So if a salt is added to water and heat is produced, meaning the solution's temperature is higher, then we know that the attraction between the ions and the partial charges of the water molecules are released much more energy than the energy absorbed to break up the attractions in part 1 and part 2. Okay, so really think about this. Okay, so if overall we see an increase in temperature because heat is produced, that means the attraction was greater and released much more energy. All right, here are separation techniques. There are really 2 we're going to focus on. Hopefully you might, if you haven't done a chromatography lab, hopefully you'll get to do one. There's some that are pretty easy and kind of fun. We can separate components in a mixture. We can separate the dyes in ink or the dyes in Kool-Aid. There's a couple of fun science and motion labs. Now, this is based on 2 things. You have a mobile phase, which is our solvent, and we have a stationary phase, which is the paper or a column. Okay, so if you put ink or Kool-Aid at the bottom of a filter paper, it soaks up some kind of solvent, and the dyes that make up the mixture travel different distances up the paper. Okay, the higher the dye travels with the solvent and up the paper tells us that that dye is more attracted to the solvent. Okay, so think about that. The dye that travels the greatest distance is most attracted to the solvent that's soaking through that paper or going through that column. Okay, and this is based on IMFs. So this is a way to separate components based on some being more polar or more nonpolar than others. Dyes that do not travel far up the paper are more attracted to the paper. So let's look at an example, and we'll talk about this retention factor. Really, retention factor is calculated by measuring the distance each dye travels divided by the total distance. So if you notice, water, in this case, is the solvent. So this person put a dot of black ink at the bottom of the paper. The water soaked. This paper would be like hanging maybe in a beaker or a test tube or something. The water traveled up the paper through the ink and noticed that the water went this high on the paper. And what happened was this black ink was actually made of 3 separate dyes. And notice how these dyes spread out. So if we measured the distance that the water traveled, and then we could take like the average distance blue traveled, the average distance fuchsia, average distance yellow. That's what we're talking about here. So if I take the average distance of that ink spot divided by the total distance that the solvent traveled, that would tell me the retention factor. So notice which dye is most attracted to the solvent. Well, it's going to be blue, the one that traveled the greatest distance up the paper. Which is most attracted to the paper? Well, it's the one that didn't travel very much. So which dye must be more polar? Now this is the key. If the solvent is polar like water, it's the dye that traveled the farthest. So in this case it would be blue. Now they could switch this. They could give you a nonpolar solvent too. The last separation technique is called distillation. Is if we had heated a mixture of liquids, we could use the differences in boiling points to collect the vapor of the liquid that boils at a lower temperature first. Okay, so again, you'd have to have the liquids in the mixture would have to have pretty different boiling points, but it's pretty cool that all you'd have to do, as you see in the graphic, heat the mixture. One of the liquids would boil first. You could collect the vapor, condense it, and it would drip into another container, and then you would have the second liquid would just remain in the beginning flask. So this also indicates intermolecular forces, because the liquid with the lower boiling point, hopefully this is starting to catch on, has weaker IMFs. It takes less energy to break. It's the one that boils first. Okay, so if we had a mixture of ethanol and water, which substance would be collected first? Well, it would be the one with the lower boiling point, because ethanol has weaker IMFs than those of water. And that concludes this first PowerPoint.